And welcome to a special, well, it's not so special, we do this all the time. Desk of Ladyada.
Yeah, wait, it is special because I got the cat.
Oh yeah? Want to see a cat?
Ha ha. Cyber cat.
Yeah, look at him.
Yeah. He was resting and then he came over here, unawares that he would be
His mistake.
on the internet. Yeah, that's cute. Hey.
Can I see him?
Okay, yeah, he's next.
Hand over the beast.
He's angry.
Yeah.
But I think he wants to be in a telephone.
What? Hi.
Phone freaker cat.
Hello.
Beep beep.
Okay.
He has his own, he doesn't have a red box or a blue box. He has a
He has a litter
Litter
box.
box.
He's a litter box. Okay, what are we doing
All
tonight?
right, sorry. Enough stupid cat humor. So we did some cool filming today, which we'll show videos later from this awesome filming we did about binary, some beginner videos. And then we came home after some Ethiopian food, and I spent a little bit of time working on the QTOUCH stuff that I've been kind of noodling with. And I spent a couple hours and actually got things going pretty well. So last we checked, I had done the decompilation for the QTOUCH code. So, you know, I had all these functions and I started rewriting them. And I rewrote them basically to, you know, this, you can't actually say like memory, you know, 04200-4C1B. Instead, what you want to do is make it a little prettier. And I actually decided to copy some of the Atmel Studio Framework methodology of talking about registers, the way they reference register locations. So if you remember, like people who have ever worked with AVRs, you have always 8-bit registers, and they were like they were basically just like pound defined. And they're pretty simple. With Atmel Studio for the SAMD processor, it's much more complicated and there's a lot of registers. So they actually did a pretty nice thing where instead of just saying this, which is like my shorthand, you know, the register conversion result is in 42004C1C and like the XY enable and like this is the flag. Instead what you do is you set up a structure. And I kind of cloned their structure setup. So for example, if you have the control A register, I just call it control A because it's like the first register you use. You create a C union type of both some bits and an 8-bit register type. And then within the bit structure, the one that's called bit, you actually put in the individual bits. Like the first bit, the lowest significant bit is SW reset, 1 bit. Second bit is enable, 1 bit. Third bit is run in standby, 1 bit, and then you have 5 padding bits because they're not used. Like a lot of these registers, you know, they're pretty empty. And this just matches what I found by kind of like looking at the code, and so you can duck down here. You can see, you know, this control A register, and I found that these were the bits that were used. These 5 bits were not used in my spreadsheet. So this is just the C language method of talking about this. And then basically you create the type. And at the very bottom, this is a technique they used. Whoa, sorry. This is a technique they used. They put all the types in order in one big structure and then cast that to the memory location. So that way you can like pretty easily access the register locations without like knowing each bit. It becomes a lot easier and a lot more readable. So the code, for example, you know, this is actually an example of some code that they use in ASF, for example, to set the pin configuration. So you see it's instead of like figuring out the bit location and then like shifting and like ORing and ANDing, you can use union, you know, and indexing and union dots to get to the location you want and then set that register. And so that's what I'm mimicking here. So for example, if you want to enable the WCO interrupt, again, I actually don't even know what WCO stands for. I haven't quite figured that one out. But when you have to set that up, you just say, you know, QTOUCH PTC, and then you point to the int enable register bit WCO and set that to 1. Actually, this is, yeah, and then for disable, it's a different register. It's the int disable. I don't know why they did that. The integer enable and disable are 2 separate locations. And then for you know, stuff like the sync config, you can read the whole register and AND it or you can read the bit location. For reasons I'm not exactly sure, my bit location addressing isn't working, and I think there's just some like detail I'm missing about like setting it to volatile or some little twiddle I'm not doing quite right. So I'm not able to use this style where I actually address each bit. Instead, I have to access the register. I don't know. I'll take a look at it later. But for now, I've just converted all of my prettier bit style references to the address location with I just reference the entire register. So instead of setting the convert bit to 1, I just OR the entire register with that bit. So whatever. And then I can read that register by just reading it as a variable. So it's a kind of a nice and elegant way of accessing address locations, and it takes a little bit more work, but I actually kind of like it because you set up the union structure once, and then you don't have to worry about like accidentally hitting the wrong bit or ORing or ANDing. It gets rid of a lot of the ugly bitwise stuff that can kind of snarl your code up and makes it hard to read and hard to debug. So I'm going to figure out what I did wrong with that bit notation stuff so I can get back to this. But basically, so I went through and I didn't do a full rewrite of all the code line by line because there's a lot of referencing to the configuration, like the you have a series resistor and you have a compensation capacitor. I'm not going to worry about that yet. I'm going to get into the details of how I want to configure it. I basically just wanted to get it going, like get the right register enabling and whatever to have the peripheral work. Once the peripheral works, I'll go in, I'll be like, okay, what's the optimal register for, speed and power usage? I think it's best to kind of get the big picture working, and then you go in and you can fix the details. It also makes it so you can always go back and make sure your stuff works. So the only thing that I basically wrote from scratch was the PTC config IO pin. So it was like so messy in the decompiled code. Let's see, it was called PTC config IO pin. Oh, sorry.
Shout out to Indonesia tonight.
Shout out to Indonesia. So it just got like kind of messy in here in this code. There's like a lot of like unknown variables and there's like a lot of bitwise stuff and labels. And I was like, well, look, I actually know what you're going to do. If you have a function called, config IO pin, it's like every config IO pin from now until the end of time on a microcontroller. You're going to set the direction, the strength of the pin, if necessary, multiplexing, making it actually use the peripheral you want. You basically have to tell the peripheral what pin to use and then also the pin what peripheral to use, right? You have to kind of set both. So I just rewrote that from scratch because it's pretty straightforward. You can check this out if you look at the pin table for, let me shrink this a little bit. If you look at the pin table for these processors, for every pin, you have the multiplex capabilities, all the different things you can do. You can set it to be an interrupt, you can set it to be an analog digital input, or a PTC or a DAC, or a SIRCOM, or a timer, or like some general clock I/O. What's interesting to me is that there's A, B, C, D, E, F, G, H type peripherals that you can set for the pin. But the B peripheral is actually kind of all the same thing. It's analog reference, analog digital converter, analog comparator, peripheral touch controller, DAC, which is only one pin, so it's like a super special case anyways. And then, SIRCOM is a different. So all of these B-type peripherals, it's all analog input. This is what kind of cemented to me, like, okay, the peripheral touch controller really is just like latched onto the analog digital converter. Like it's setting up the pin to do something and it's doing analog reads to actually do the conversion, but it takes over the analog peripheral for a time. It's just sort of a symbiotic relationship. I don't know. But again, I don't know the details because I didn't publish any details. So after you set up the mux and everything, you actually don't have to do much more after you configure the I/O pin. Because I'm not doing mutual capacitance, I'm not doing the grid, I'm doing single point capacitance. You just say PTC acquire. So let's close this up and let's see, get this into a nice location here. So let's look at, again, what this looks like on the oscilloscope before I start my code. So we can go to our oscilloscope. It's great for looking at voltages.
I have a question for you, though, Ladyada.
Yes.
Well, what does the oscilloscope kind of do?
It's good for visualizing frequencies and waveforms, measuring frequencies, stuff like that.
Yeah?
Yeah. Voltages may be better to measure with a multimeter because maybe they don't move so much.
Yeah.
Or current, you can measure with a multimeter, but for frequency and waveform, you want to use an
I
oscilloscope.
think Silly the oscilloscope has something to say.
Well, like Ladyada was saying, frequency is how often something happens over time. And we measure frequency in units called hertz.
All right, so let's do this.
Thanks, Silly the oscilloscope. Okay, so
Today's magic word is oscilloscope.
so
When you hear oscilloscope, scream real loud. Oscilloscope.
okay, let me see.
Can you scream real loud? Okay.
But I want to just move this a little bit. We'll resync Silly later. Okay, so in this example, I'm taking 2 capacitive touch measurements, and you can see that I take 16 measurements. It just means that it takes a little longer to get measurements, and then they average them out. But in my opinion, it's just gives me a little more time to do the printouts of the data that I grab the register data while it's doing it. So this is one channel, and then this is the other channel. And you see they happen one after the other. And when I saw this, you have 2 measurements, and this is the library doing it, not my code, I could tell, oh, you're really just doing 1 measurement at a time. Okay, cool. I'm just going to make my code do 1 measurement at a time, too. Usually what you do in the library, which is kind of a pro and kind of a con, is you actually tell it all the pins you want to measure, and when you tell it to do a measurement, it measures all of the pins in series. So if you have 16 self-capacitive touch pins, it'll actually measure all of them and then give you all of the readings at once. You can't really tell it to do only 1 at a time. It's like not, I mean, you can, but it's like really complicated to do so. What I like about my code is that I won't have to do this because I have full control over it. I can take all the measurements at once, or I can just take 1 measurement at once. Okay, so then let's go back to my code stuff. So the code I wrote is really basic to start. Instead of using the interrupts, I actually don't use them at all because interrupts just makes things more complicated, makes it harder for me to know. Like I want to be able to, I was going to pull it. You can always add interrupts later. Again, you can always tune the resistor, tune the capacitor, tune the power usage, make it do multiple reads at a time. Right now, I want to read 1 thing at once, and then I'll just pull and wait for it to finish. So here's where I kick it off. Touch self-cap measure, sensors measure, enables the PTC, configures that pin to be the peripheral for touch, and then actually starts the conversion by setting a bit in a register. And then just for like my sanity, I have these functions that snapshot the registers and print them out. It's just it's like a printf debug. It just takes a snapshot of these register locations because then I can compare what my registers are to what the library sets them to, and I can sort of check, do mine line up? And then I'm polling here. I'm waiting until this bit is no longer set in the control register. It's pretty common to have registers where you set the bit and then you read the bit to wait, and the microcontroller will set it to 0 when it's done. That's a kind of a common idiom. And then when it's done, this is just kind of gross, but I actually just cast the address locations for the conversion result and added the 2 together, the low and the high, and I print out the result. Pretty simple. So let's continue running the library code that does the 2 measurements for me, and I'll just add my register read, my conversion read at the end. Do you have any questions? Or?
We're going to take some questions at the end.
Okay.
Because there are some questions that have nothing to do with what we're showing. So
Okay.
I figured we would show all things you want to show.
Okay, so let's go to the oscilloscope.
Yeah. I'm going to do that in a second.
Okay.
but I kind of want to do something else first.
Okay, thanks. Okay, so now that I've got my code running, you see these are the two reads from the library, and then this read over here is my read. So there's a big delay because I'm printing out all the registers, doing a bunch of debugging stuff, and like saying like, did that work or not? And also I wait for the interrupt to end. So like, here's actually where I start printing out stuff, and then this is where I actually start the conversion. So that's why there's a big gap. It's just a bunch of debug printfs that have to finish. So the good news is I've got the waveform I want, right? This looks pretty right. I can look at it in detail. Yeah, we got the 16 readings there, and then you can see the this little purple blip is when I do the register snapshot. That kind of tells me when it happened. Can look at the registers. It's not too exciting. What I want to do is look at the data readouts to make sure that they make sense. So when we go to the computer, this is going to be computer fun time. Okay, so this is my code. So I'm going to say like, okay, I'm trying to do this myself. I'm just checking the register values, and then I say, okay, acquiring. I check another register. I do that register printout. Again, all this stuff's going to get deleted. It's just for me debugging while I figure this out. I have a notepad here with what the conversion registers are supposed to be when the library that I don't have access to does it. And, I went through and I was like, okay, do these numbers all look the same? Just making sure I didn't miss anything. Yeah, what's up?
So what code are you writing all this in?
This is all in C++, which is, pretty standard. And the code that the code I'm decompiling was also written in C++. But the good news is that once I get this working, we're going to make it work in MicroPython and CircuitPython and stuff too. Okay, so after I started the acquisition, somewhere down here, the conversion ended. So it took a little bit of time, but I got 16255. And then this is actually the other conversion. So I'm going to update the code to make it a little clearer. Okay. And then up here, I'm going to say, using QTOUCH lib to read. Okay, so this will make the printout a little bit easier to understand. While your code is compiling and uploads, it's a good time to drink.
Tonight's alcoholic beverage is brought to you by a Next coffee mug I got on eBay.
Yeah, check
Next
this
coffee
out.
mug. When you don't know anything else to do, get a Next coffee mug.
Nice. Okay, so we're back. Okay, so now, so the QTOUCH library gets us these signals. And then when I do this myself, this is my code that's running, I get these big numbers. Now, one of the reasons I'm getting big numbers is I'm not dividing by 16. What the library does is it takes those 16 samples, like all those little notches you saw, and then divides by 16. I'm not doing that because, again, I can always do that later. Now, the number is pretty high. And the reason the number is pretty high is actually because it's connected to my oscilloscope. Every oscilloscope probe has some capacitance and resistance to it. Now, actually, it's not that much capacitance, but I have the peripheral slowed down, and so there's a couple little things that are making it so that when the capacitor probe is on there, it actually reads quite a high value. So what I'm going to do is I'm going to remove the capacitor probe. Can you handle it?
No.
Well, tough. So when I remove the capacitor probe, my conversion gives me 23, which is like a much lower number because, again, there's nothing it detected. It's like 20. It's basically 0, 3. And now I'm going to try touching it with my hand. So when I touch it, it goes back up to 12,000. When I let go, it's like 37. When I grab it and hold it really, really tight, it's 13,000. What if I just like touch it kind of lightly? When I touch it kind of lightly, I get like 298. So the good news is that now that I have things kind of working, what I'm going to do is flesh out my library, because right now it's like, it's really kind of clunky, because I'm trying to copy what's going on in that decompiled code. What I'm going to do is make it, a little more elegant. Instead of having like 15 functions, I'm going to have just like, I'm just going to have it all happen really in one function. I'm also going to let you set up the series resistor and series capacitance. But like I have a proof of concept working. I also have to get the initialization stuff decompiled and reverse engineered, setting up those initial registers. But that code is much simpler. Like I looked at the function and it's like, for self-capacitance, it's really only like 4 or 5 things I have to do. And then what I can do after that is in my circuit playground design, because this is what this is all about. So circuit playground rev E. What I can do is, whoa, nope, yep, nope, nope, is get rid of like this resistor pack and this resistor pack, because these were only there to help do the capacitive touch sensing by using that simplistic resistor capacitor sort of decay function, like measuring how long it takes to decay. Without needing that, if I can use that built-in peripheral, and it seems like I got pretty good data out of it, as good as I would get if I used resistors, I can get rid of these 2 parts, and that will free up a bunch of space for me. I can move the buttons up a little bit maybe, or I can just change the routing around, because I don't have to route around these pads so much. And what I would like to do is make some space so that I can get these 2 LEDs. These are IR LEDs, and maybe get them spaced a little nicer. These are for infrared receive and transmit. And I'm kind of running out of space down here. It's getting a little like, cozy, I guess. So what I'm hoping is when I get rid of these resistor packs, it'll free up my routing space a little bit, so that I can put, what I'd really like to do is put like one of these LEDs like over here, and then the other LED like over here, and then I would move these 2 components up here perhaps, and like have them kind of come around this way. These are for the audio amplifier. And I'd like to have the IR sort of like symmetric around the accelerometer. So I might move some stuff too. Like I might move the reset button down instead of up to make it closer, but I'm not exactly sure yet. But that's my goal here. So all of that work really was just to get rid of these 2 parts. But it'll also make it possible for us to use the circuit playground with CircuitPython without needing like a lot of overhead code. Like this library linking it in is a pain. It'll be faster because I can do read 1 sensor at a time, and also I can use it with like weird linked stuff like PXT, where they don't use a compiler, they link code in. So it's like linking in an external library is complicated. So all good news, and of course Arduino as well. You can't link external libraries with Arduino, but with my code, because I'm twiddling the bits directly, it's going to work just fine.
Is the IR used to measure distance?
You can use IR for 2 things. You can, 1, measure distance with it by looking at the DC value. But with the AC value, you can use it as a remote control or remote control receiver, or communicate between circuit playgrounds. So they can have a very basic data transmission protocol.
Okay.
Yeah.
Is that it for tonight?
Mm-hmm.
All right. If we do a broadcast tomorrow, what samples are you going to show off?
Oh yeah. Well, I thought I was going to keep working on this. I didn't get to my samples, but I got some cool. Yeah, this is my Arduino Zero that I'm using as guts. I got these arcade buttons that have LEDs built in. So they've got this little LED jack here. So I thought maybe I would try these out. These are kind of nice buttons, and yeah, they're basically just like quote unquote normal arcade buttons, but they have a little slot for an LED, which I thought was cool. I don't know if any of these are RGB style. I think they're all just like single LED. And then I got some small ones that do LED too. Little miniature style. Also has a little slot for an LED.
Yeah.
Yeah.
Okay. So
I think LED arcade. I mean, like, you know, we have a hack on how you can add NeoPixels to arcade buttons, but it's a pain. This is nice because it's like you can just plug in a cable right there, maybe backlight it.
okay. So if we broadcast tomorrow, we'll show those. If
Yeah,
not,
it
it'll
would
be
be
later
it
in
would
the
be
week.
sample Sunday.
Okay.
But that's my update for today. So far, some good success with the QTOUCH reverse engineering. Next up, I'm going to just clean it up and make it prettier. And then I'll get rid of all of the library code. Like I won't, right now I'm using the QTOUCH library for initialization, but not for reading. What I'll do is I'll get rid of that initialization code too and like see if it works. If it works even like half well, it's still better than doing the resistor trick and better than linking an external library. And then I'll probably post it up on GitHub or maybe write like a little tutorial on how to use it. Because you'll be able to use it with any AtSAMD based board, including like the smaller ones or like the Feather, the Zero. You know, any board that has a SAMD will basically have capacitive touch built in on like 16 different pins, which is kind of nice.
All right. Here's a question from the chat, and then
Yeah.
we'll just.
Do some questions.
Well, no, we'll just end it after this.
Okay, one
All right.
question.
Okay, so how can a person make a phone charger from an 18-volt, 15-amp solar panel?
Well, you'll want to get whatever charge controller is for that panel. So that panel probably has a recommended, you know, lead acid charge controller or something, and then you can connect a battery to it, and then you would use like a buck converter from that battery. So you need to have a battery. You can't connect it directly to your phone. It's just like not a good idea.
Okay.
It's better to charge a battery, and then whatever battery it's charging, use that to charge
500
your device.
milliamp is the answer to the question.
Well, but you need the controller. Like you
Okay.
need the charge controller for the battery. There's something that takes a solar panel and charges the battery. Wherever you got that solar panel from, they probably also sell the charger.
Okay, you ready?
Yeah.
Do another question. Someone were to do a talk at a code conference in March on the NeoPixel library. What NeoPixel hardware would be the best for a demo?
A NeoPixel ring is good, and like an Arduino or any Arduino compatible. People really like the rings, so I would get like a ring or a strip. Like a 1 meter strip is good.
Okay. All right. Well, that's it for tonight, everyone. Thank you so much for tuning in. This is Desk of Ladyada. If you want to support open source hardware companies like Adafruit, go to adafruit.com. Purchase some electronics. We very much appreciate it. And we'll keep doing this as long as we can pay the bills. We'll be doing this maybe some Desk of Ladyada before Wednesday. But Wednesday, 7:30 p.m. Eastern Time is Show and Tell, Show Your Projects. 8 p.m., Ask an Engineer. And now, closing Desk of Ladyada tonight, Silly, the oscilloscope, is going to do some talking.
Okay.
Yeah, we're going to see how this goes.
I'm gonna have to move this back a little bit.
What are you going to move? What are you going to do? What are you doing?
I had to shift it a teeny bit.
You
once.
shifted a teeny bit?
Yeah.
Do you know where you shifted from?
No.
Oh,
It
man.
was not. It was not showing up well.
That's all right. We'll do it live.
Oh, we'll see what happens.
Go back to work. Go back to work. Make more electronics. Go back to work. Go back to work. Read more RSS feeds about electronics. Use me. Abuse me. Frequently. Frequency.